You won't find many piston guys that understand rings, and even less rotary guys that understand seals. So I'll go through the modern techniques of piston ring control and we'll transfer that to the rotary engine. I've exaggerated the ring grooves for clarity, but this is our modern piston and ring design. The top ring is the compression ring. The second ring is not a compression ring, like everyone believes, but actually an oil scraper. And the third ring is the oil control stack. The compression ring is the most important and is under the most stress. And they mainly use differential pressure to affect the seal by being pushed onto their mating surface, same as any reed valve or shim valve. And the way it works is, after ignition the pressure rises in the chamber, the pressure then goes down between the gap between the piston and bore and presses hard on the piston ring, and this presses the ring hard on the ring land, effectively making a seal on the bottom. The gases then get behind the ring and push it out towards the bore, affecting a seal on the side. Anything that increases the pressure differential across the ring or reduces the lag of the pressure getting there will increase the seal and hence make more power. Pressure delay is because gas can only leak at a rate dependent on area due to it being limited by the speed of sound. One way to increase pressure to the ring is drill vertical gas ports. With vertical gas ports they usually run a tighter ring to groove clearance so it traps gas behind the ring, which makes even more power. Vertical gas ports are only good for race motors because they're rebuilt so often the holes are always kept clean. But for the street you'd go lateral gas ports. These are holes drilled from the side that end up kind of a half hole. Some ring manufacturers sell groove rings to achieve the same effect. Gas ports gets pressure to the rings faster, but another way to do it is move your ring stack closer to the top. But the problem with moving the ring closer to the top is that it overheats sooner and loses its spring tension. Ray and Morrison tested this incrementally all the way to 1 mil from the top, and each time it made more power. But at 1 mil, the rings would overheat after 6 pulls on the dyno and the engine would start losing power. And that was with the hardest and strongest pro-stock piston rings you could get. Another way to increase differential pressure across a ring is to induce a vacuum in the crankcase. The simplest one is the positive crankcase ventilation valve, which uses intake vacuum. The EVAC or vacuum pan that uses an angled stub on the exhaust. This uses exhaust velocity to lower the pressure in the angled branch. This requires a one-way valve to stop exhaust returning to the crankcase. Next is the performance vacuum pump. These pumps are the serious ends of the performance world, and our dyno operator always saw a gain with them. It's okay to run these vacuum pumps with up to 15 inches of mercury without modifications, but when set to high vacuum levels can pull oil off parts, so you have to feed oil directly to them. Things like center drilled conrods that feed oil directly to the pin. Also you might have to fit your seals backwards to stop air getting into the crankcase rather than oil getting out. We gained about 15 horsepower on a 600 horsepower engine when set to about 12 inches mercury. And lastly there's multi-stage dry sump oil pumps that scavenge so hard they create a vacuum as well. Another way to increase effective seal is to make the rings more flexible, so they can change shape and seat on surfaces better. That's why there's been a reduction in the thickness of rings and seals. This is only possible due to the use of harder materials. Piston rings went one further and actually reduced the radial depth. Of course this requires an accompanying shallow groove. You can see less radial depth in this piston. If you're running deep groove pistons and you want to put these narrow rings in there, you have to put a stuffer in behind them. The empty void acts like an accumulator and delays the pressure building up behind the ring. Next is the second ring, the most misunderstood ring in the pack. It was so misunderstood even the ring manufacturers were getting it wrong for decades and only started fixing it in the last 30 years. What they were doing wrong was they were using it as a second compression ring. In the old days, if they thought their rings weren't sealing enough, they'd just add more rings, like this Rolls-Royce Merlin engine with 4 rings. But then they discovered that the gas leaking past the top ring would get trapped on top of the second ring, and that would lift the top ring off its land, effectively making the top ring redundant because all the pressure was now leaking past it and going onto the second ring. Basically it became a power-robbing passenger. And the way they try to stop the second ring trapping gas is to make sure it has the same ring gap as the top ring. Basically if you get a set of rings where the second ring gap is smaller than the top, you've probably got an old set of rings. This is why the evolution of the Merlin engine went from 4 ring to 3 ring. This extra oil control ring is due to planes being able to fly upside down. Mazda did the same thing in the late 60s with twin side seals, but they quickly threw one out by the early 70s. The piston manufacturers also came to the party and they put an accumulator groove between the top and second ring. This delays pressure build-up due to the larger volume. You can put the rings further apart and get the same effect, but generally ring stacks are getting shorter because the piston pin is moving up due to longer rods. Mazda had something similar 20 years earlier and it's called the blow-by recovery groove. Mazda originally had flat-sided rotors, but they were having a lot of trouble sealing the different zones from each other. They were getting exhaust in the oil and oil in the chamber, hence why they went to twin side seals and even triple oil control rings. They were even having problems with the rotor lands wearing out because the rotor was being pushed to one side, and this was due to the blow-by pressure getting trapped on the side of the rotor and pushing the rotor to the opposite plate. So they cut a blow-by recovery groove, which always hangs over the inlet port no matter where the rotary is, and that equalised the pressure and all their problems went away. It even allowed them to get rid of their second side seal and third oil control ring. The popular design for the second ring these days is the Napier ring, with its sharp edge and hook that scrapes oil very effectively. And the last ring on the piston is the oil control set. The oil control ring set is basically the same, just with thinner rings and a smaller package. Just to iterate a bit more on the second ring being a compression ring falsehood, by the mid-90s pretty much everyone knew the second ring had to leak to make more power, but Total Seal continued to make a gapless second ring for another decade, and this caused problems for people who didn't know. I had just ported the cylinder head on the red car, which moved it to the front of the field, and even though it's behind the V8s on this power circuit, on small circuits it would routinely beat them. And I went to his workshop to measure some parts so I could run a simulation of his engine, and the first thing I saw was boxes of Total Seal rings next to his pistons. I told him to throw them away and go to a gapped second ring, but he was reluctant, because what could be better than a ring that doesn't leak? But when he eventually did go to a gapped second ring, he came back to thank me. The engine was blowing out so much oil, due to the top ring not holding any compression, that it used to fill his oversized catch can right to the top that it had to be drained out between races. But after he switched to a gapped second ring, the catch can stayed bone dry. And on top of fixing that problem, at the dyno it made more power as well. I think Total Seal saw their error and eventually went with a gapless top ring. To follow that along, there's a story of an engine builder in the US who was developing motorcycle engines. He did a mod to an engine, but when he put it on the dyno it lost power. Most people say that mod didn't work, so I won't use it. But this guy was sure it should have worked. So a lot of head scratching later, he started taking the motor apart. Everything looked normal until he got to the piston, where he saw carbon down the sides of the skirt past the rings. That's when he realised he was making more power, it's just the rings couldn't hold that power level anymore. He redesigned the ring pack and made more power, but he needed to catch the problem on the dyno, and that's where he came up with the idea of putting a blow-by meter on the crankcase. Basically, if you're making the same power but there's more blow-by, you're probably actually making more power. We talked about how they increase the seal efficiency in an engine, now let's talk about how they reduce the friction. This doesn't really apply to the rotary engine, other than they made their seals narrower in 85 and that reduced the friction a little bit, but for a piston rubbing on a bore, there was more power to be found. Originally pistons were just cylinder shaped. Then someone figured out if we can reduce the friction of the skirt on the bore, we can make more power. So they started putting anti-friction coatings on the skirt on the thrust sides. Then they figured if we can reduce the size of the skirt, we can make even more power. And that resulted in these tiny pistons with tight ring packs close to the top and high pins that make the skirts even shorter. They even changed all the cross-ribbing support under the piston and made the pin half the length. As per usual, F1 uses extreme examples, and if you look closely, it's only a two-ring design. Less rings, less friction, so more power. It's unlikely you can run a two-ring system without some sort of vacuum in the crankcase, and it kind of explains why they smoke on engine startup. We did do some street testing of a two-ring piston designed from our major piston manufacturer, but they didn't work that good. Basically it smoked a little and you needed a massive top ring gap to stop the rings butting. As a matter of interest, I think Pro Stock are still achieving a higher piston speed than F1 even though they're only running half the RPM, and that's because the piston has to travel 3 times the distance. Another way to reduce friction is to use low tension rings. In actual fact, ring tension is only relatable to the oil control ring set, which comes in different grades of tension. But when you go to a thinner ring, there's less cross-sectional area, so there's less springiness in it. The usual way to measure ring tension is hook a spring scale on the piston and drag it through the bore with the rings fitted. As an amusing story from an engine builder from a SEMA show 30 years ago, he told us that one of his customers needed a set of pistons for a race on Christmas Day, but because all the piston manufacturers were closed, he rang up this engine builder to see if he had a set of pistons. The engine builder had a set of piston blanks that required machining. The problem was pistons aren't round, so he asked his machinist if he can machine it, and he said yes, he can do it on the mill. The problem is when you machine something round in a mill, the side gets made up of little flats. Basically the piston looked like a stop sign. So he rings the customer and says the pistons are ruined, but the customer said so long as it seals gas, send them up, even if he finishes last. So he packed up the pistons and sent them to him. So the race comes and goes, and after a week there's still no word from the customer. So he rings him to see what happened. Well, the customer said the pistons were fantastic. They made 8 more horsepower than they ever did before, and in the race they finished 5th. The highest position he's ever finished in. The pistons were the only things the customer changed, so running on those sharp edges reduced the piston friction and made more power. Another thing about piston rings is they twist with the motion of the piston. When the piston goes up, they twist down, and when the piston goes down, they twist up. The top ring is barrel shaped, so it's designed to go up and down, but when it has pressure on it, it's usually in the down position. The other rings aren't supposed to have pressure on them, so they're twisting all the time. As a performance engine builder, you can learn a lot about what's going on inside an engine by looking at the used parts in fine detail. Like shiny spots means it has contact, and matte spots means it hasn't. So next time you take your engine apart, wash the old parts and see what they tell you. This video ended up too long, so I'm going to split it into two parts, and the second half will probably only be the rotary and how all this relates to it.